Hi everyone. If you didn't get a chance to meet me at Katie, my name is Tim Lycurgus and I am a postdoc here at D3C, working with Danny on smart designs. And today I'm going to be talking to all of you about clustered smarts, which is hopefully pretty exciting given we're all education researchers with, that natural clustering that goes on in education settings. So throughout this module, you're going to learn what's different in a clustered smart and compared to standard smarts with respect to new data analytics, new sample size considerations, and new software used to analyze clustered smarts. So this module is going to proceed as follows. We're going to start by talking about clustered adaptive interventions, or clustered AIs, and their similarities and differences to standard adaptive interventions. Then we'll move on to clustered smarts and their similarities and differences to standard smarts. Then we'll talk about the new data analytics that arise due to the clustered nature of the data, and then end with new software used to analyze these clustered smarts. So beginning with clustered adaptive interventions. So as I'm sure you were all aware, in education, interventions are frequently going to take place at the cluster level. So for example, a school or classroom level intervention. And while the interventions occur at the cluster level, they are frequently designed to improve outcomes for units that are nested within a cluster. So for example, we could have coaching of school professionals to help children with mental health problems, or school-wide positive behavior supports in general education. Of course, these are just two examples. There's many, many others I'm sure you can all think of. And just as standard interventions can be adaptive, so too can clustered interventions be adaptive. And why might you want to do that? Well, by adapting and readapting these cluster level interventions, hopefully you can improve outcomes for the greatest number of units nested within that cluster because you're tailoring to the specific needs of the cluster. So that leads to our definition of a clustered AI, which is going to look pretty similar to what you've seen for standard adaptive interventions. A clustered AI is just a pre-specified set of decision rules that guides how best to serve the baseline and ongoing needs of clusters from a pre-specified population. So to talk about clustered AIs, we're going to look at the following as our motivating example. It's a clustered adaptive intervention for implementing cognitive behavioral therapy, or CBT, in school settings. So a very brief overview of this clustered AI. The school starts with in-person training plus rep. After 2 months, they get rep plus coaching. They get that for 2 more months, and then based on how they're responding to rep plus coaching, they either continue with rep plus coaching or they augment with facilitation as well. So before diving in more deeply, what are these intervention options? So REP is Replicating Effectiveness Program. This is a didactic training in CBT for all school mental health staff, and then technical assistance for school professionals as they need it. Coaching is just a skills training to improve the competence of the school professionals in providing CBT. And then facilitation provides schools with opportunities to discuss barriers to CBT delivery in school settings with a facilitator. So what does that mean? Well, maybe there's not buy-in from the school administration or the principal. They don't think it's worth it to provide CBT, so they're not providing resources for these school professionals. In settings like that, maybe facilitation helps overcome those barriers to CBT delivery. I should also say, what do I mean by school professionals? School professionals could be, guidance counselors, school psychologists, social workers, etc. We're going to group them all together and call them school professionals. So taking a brief step back, what are the components of a clustered adaptive intervention? Well, we still have 5 components as we did with standard AIs, and they're actually going to be the same. The difference is we're going to have new design considerations when talking about each of these 5 points that we didn't have when talking about standard adaptive interventions. So our 5 components are the proximal and distal outcomes, our decision points, our intervention options, tailoring variables, and then decision rules. So we're going to talk about all 5 of these in the context of the clustered AI we just looked at. So first, proximal and distal outcomes. For this clustered adaptive intervention, our proximal outcome, so our primary goal, was to increase the number of CBT sessions delivered by school professionals within the school. So this proximal outcome is at the school professional level, nested within schools. So you can already see how we have this cluster data cropping up. Our distal outcome, one of them is also at the school professional level, and it's to improve CBT knowledge and skills of those school professionals within the school. So once again, school professionals nested within schools. But when you think about this, well, why do we want to provide more CBT? Well, it's to improve the anxiety levels for students who need that CBT. So our ultimate goal is this distal outcome, which is at the student level, and it's to reduce anxiety levels among these students. So we have an additional layer of nesting here. We have students nested within school professionals, nested within schools. So you can see how that's different from standard adaptive interventions where the intervention occurs at the same level as the outcome. Next, we have decision points, and in this case, decision points really aren't that different from decision points in standard adaptive interventions. We have ones at 0 months, 2 months, and 4 months. Obviously, month 4 is the non-trivial, more interesting decision point. The only distinction here is the decision is being made at this decision point for the entire school. But we'll get into that in more detail in just a couple slides. So we already talked about intervention options. In this case, it's rep, coaching, and facilitation. But I do want to point out that all of these interventions are cluster level interventions. So the entire school will receive rep plus coaching, and then if they need the additional treatment, the entire school will augment with facilitation. It's not like just individual school professionals are receiving the augmented treatment. All of these interventions are school level interventions, so the entire cluster receives it. Next, we have tailoring variables. So we actually have 2 tailoring variables, and there are some special considerations here as well. So the first tailoring variable is the amount of CBT provided by a school professional, and the second one is the number of barriers to delivery identified by the school professional. Now note, those variables are tracked at the school professional level, but the decision needs to be made for the entire school, because the entire school receives the same tailored treatment. So what we do is we're going to aggregate those variables up to the school level. So our actual tailoring variable is going to be a binary 0-1 variable. It's either every school professional in the school has provided 3 or more CBT sessions to at least 10 students, or they haven't. And likewise, either every school professional has identified fewer than 2 barriers to delivery, or they haven't. So you can see, it's this 0-1 aggregation of those school professional level variables up to the school level. And we'll talk about these varying levels for tailoring variables later on in this talk as well. I also want to point out that a tailoring variable is forward-looking, and that we're tailoring the clustered AI to improve end-of-study outcomes. That being said, it's also affected by prior intervention, in the sense that when we're constructing this tailoring variable, in a way it's to help us answer the question of, is the school responding favorably to rep plus coaching? So it's both designed to improve future outcomes, but affected by prior intervention. So it kind of goes in both directions. Then lastly, we have decision rules. So in this case, our decision rule is either if every school professional at the school has delivered 3 or more CBT sessions to more than 10 students, and every school professional has identified fewer than 2 barriers to delivery, then we're going to say they're responding well, and we're going to continue with just rep plus coaching. On the other hand, if any school professional is not providing sufficient CBT to 10 or more students, or a single school professional has identified 2 or more barriers to delivery, then we're going to say the entire school is eligible to receive the more intensive intervention of rep plus coaching plus facilitation. So as I, alluded to earlier, this decision is made for the entire school rather than for the school professionals because these are clustered interventions. Okay? So you can see how, we're already using individual outcomes aggregated up to the cluster level to make the decision for the entire cluster. So it's a distinction to standard adaptive interventions. So maybe we would say, we like that clustered adaptive intervention that we've been talking about. We think it's optimal, so we can just proceed with a confirmatory trial. But it's probably more likely that as education scientists, we're going to have a bunch of questions we want to answer to improve on that clustered adaptive intervention. So essentially, how can we do better than the clustered AI we've been talking about? And to do that, we can ask some of the following optimization questions. So we could ask, what is the effect of offering versus not offering coaching in the first stage of the intervention? Or we could ask, among schools who are not responding favorably to the initial intervention, should we add on facilitation or not? Or we could ask, should we offer both coaching and facilitation in those first 2 stages, or shouldn't we not offer either of the 2? So those are standard questions we ask when optimizing these clustered adaptive interventions, but we can get more in depth also. We can use more of the science. So some other possibilities are, is it possible that first stage interventions have no effect in the short run, but are going to have beneficial effects in the long run when followed by a particular second stage strategy? Or maybe when we sit down and think about what facilitation is actually doing, we might think, well, in high resource school districts, there's not much of an opportunity cost to offering facilitation or to offering CBT in addition to, other priorities of the school. So even if, administration doesn't, love the idea of setting aside resources for CBT, it doesn't pull away resources from other priorities of the principal. So maybe those barriers to delivery don't really show up in school districts with higher resources. On the other hand, in lower resource school districts, there probably is more of an opportunity cost. If you're setting aside rooms and resources to provide CBT to students in need, you might be taking those resources away from other goals. So maybe there are more barriers to delivery in those lower resource school districts. So we could ask, should facilitation only be offered to suboptimally responding schools within lower resource school districts? So these are just 2 possibilities of questions you could ask. I'm sure if you guys just sat here for 10 minutes, you could come up with many others that, could really be used to enrich this clustered adaptive intervention. So now that we've had a review of clustered adaptive interventions, we're going to dive into clustered smarts. So a clustered smart can help us answer all of those optimization questions we just talked about. And they're like our standard smarts, just we have those randomizations at the cluster level and outcomes nested within clusters. And unsurprisingly, these are used to optimize clustered adaptive interventions. So our motivating example is going to be adaptive school-based implementation of CBT, or ASIC, which is a clustered smart designed to optimize clustered AIs aimed at increasing delivery of CBT in school settings. So I know Annalie talked about this in our case studies module a little bit, but I know it's also been a month since Katie, so I'm going to give a brief recap of what ASIC looked like. So the idea behind this was Michigan high schools are required to have staff on hand who can help with the mental health needs of students. But if you look at what's actually going on in Michigan high schools, they're not really following evidence-based practices. So the idea behind this clustered adaptive intervention to increase CBT delivery is, well, this will at least give them the tools to provide students who are in need with an evidence-based practice, that is CBT. So anyway, ASIC takes place in 94 high schools in Michigan with not quite 200 school professionals. Each high school has between 1 to 3 school professionals, and our primary outcome is going to be the number of CBT sessions delivered by each school professional nested within each school. So this is what ASIC looks like, and I'll walk you through it. So every high school gets a 3-month run-in period of a rep, and then they get randomized with equal probability to either receive rep or rep plus coaching in the first stage. That happens for 2 or 3 months, and then we check their response status. So if they are responding favorably to their initial treatment, they're ineligible for augmented treatment, and they're going to continue with either rep or rep plus coaching, depending on what their first stage treatment was. Among those schools that are responding a bit slower, well, they are eligible for the intensified treatment. So they're going to get re-randomized, once again with 50% probability, to either continue with their first stage treatment or to augment with facilitation. We track that for about a year, and then the study ends. So, just as with standard SMARTs, there are 3 common primary aims in a clustered SMART. So, aim type 1 is to compare the main effect of the initial intervention options, so rep or rep plus coaching. And to do that, you would compare all schools consistent with any of those red boxes, so A, B, or C, with all the schools consistent with any of the blue boxes of D, E, or F. Aim type 2, we could compare the main effect of second stage intervention options among the non-responders. So that would be comparing the red versus the blue. Obviously, the responders are in gray because they don't pop up here. And it would be continuing your first stage treatment versus supplementing with facilitation. So boxes B and E would be compared to boxes C and F. Or we could use aim type 3 of comparing embedded clustered adaptive interventions. And this was actually ASIC's primary aim. It was to compare that most intensive clustered AI. This actually corresponds with what we were looking at earlier in the blue, of rep plus coaching in the first stage. Responders continue with rep plus coaching. Slower responders supplement with facilitation. So compare that most intensive clustered adaptive intervention with the clustered intervention of rep only, which is in red. Note, I'm just calling this a clustered intervention instead of clustered adaptive intervention because they receive rep no matter what, so no adaptation is going on here. Of course, these are just 2 of the 4 embedded clustered adaptive interventions embedded within ASIC. Obviously, we could compare any of the 4. We also have a more common secondary aim in clustered SMARTs, as it is in standard SMARTs. This is aim type 4, and it's to construct a more deeply tailored adaptive intervention. And we can do that using moderator analyses like we saw Mason talk about in Module 7 to help address this aim. Now, this moderator analysis could be used to inform the choice of additional tailoring variables, or potentially to inform the choice of cutoffs for an existing tailoring variable. So, I'm not going to recap those moderator analyses. Mason did a fantastic job already. But there are some things you should keep in mind that are different about this more deeply tailored AI portion and a clustered SMART compared to a standard SMART. So, it is not going to be sensible to examine whether a lower level candidate tailoring variable moderates the effect of a higher level intervention. So you don't want to use individual student improvement to see as a tailoring variable for a classroom level intervention. Why is that? Well, one student would be making the decision for the entire class, and which student is it? It doesn't make much sense. That being said, you could examine whether a higher level candidate tailoring variable, so for example, urbanicity of the school, moderates the effect of a lower level intervention, like a classroom level intervention. So you don't want to go bottom up, but you can go top down. You could also examine whether some aggregated lower level candidate tailoring variable moderates the effect of a higher level intervention. So you could use average student improvement at the classroom level to see how that moderates the effect of a classroom level intervention. So this is actually what we were doing in ASIC, where we used an aggregate of school professional level data to make a decision for the entire cluster rather than using, individual level data itself. So now that we've reviewed clustered smarts, hopefully that looked, somewhat familiar to all of you because they don't deviate too much in that sense from standard smarts. But now we're going to have some new data analytics we need to get through because this is where clustered smarts are really deviating from standard smarts. So by new methods, what do I mean? Well, now we're going to have new modeling considerations. We're going to have new estimation considerations. There will be finite sample adjustments and the new sample size formula when you're designing your clustered smart. And all of these innovations are needed due to the multi-level structure of our data. So in standard smart designs, everything's occurring at the same level. So we have the treatments provided at the same level as the randomizations, at the same level as the outcomes, etc., etc. But in clustered smarts, we have units nested within clusters. So in ASIC, we have the intervention and the randomizations at the school level, but our outcomes are at the cluster level, school professionals nested within schools. So in practice, that means we're going to need to account for the correlation structure in some capacity, and we also need new software so that we can account for this nested structure when we're analyzing data from a clustered smart. So that leads to the ICC, which is a term you're all probably at least somewhat familiar with given you're all in education. But with clustered smarts, we're going to expect outcomes to be correlated within schools, which leads to our interclass correlation, which is just a measure of how similar outcomes of units are to one another within a given cluster. So why would we have that? Well, in the context of CBT delivery in schools, it's probably likely that the amount of CBT delivered by school professional A in a school is going to be correlated with the amount delivered by school professional B in that same school. Of course, only correlated within schools, not across schools. We don't think, if I'm providing CBT in school 1, that amount is going to be correlated with the amount that Mason is providing in school 10, for example. But within a school, they probably will be correlated. And if you look at two extreme examples, I think we can see that. So imagine a school where every single kid has anxiety and requires CBT. Well, if every kid requires it, this is probably a pretty big issue. So every school professional in that school is probably providing some amount of CBT, of course, given they are, qualified to provide CBT. So they're going to be pretty correlated in the sense that they're all providing a good amount. On the other hand, we could have a school where not a single kid has anxiety or requires CBT. And I'm not saying that ever happens, but in such a school, well, if nobody requires it, probably school professionals aren't providing any CBT. So they're going to be very clustered at 0 CBT provided. In reality, we're going to be somewhere in between those two extremes. And, some school professionals are going to provide more than others, but there's probably some correlation. So that is going to lead to new modeling considerations. And these next 4 or 5 slides are going to be a little mathy, so bear with me. Hopefully I'll make it so that this is, somewhat interpretable and not too miserable for all of you. So let's say y of ij is our outcome of school professional I in school J under adaptive intervention A1, A2. And we can model that outcome as follows: beta 0 plus beta 1 A1 plus beta 2 A2 plus beta 3 A1 A2. All of that is our marginal structural mean model, which will denote mu of A1 A2. And now you can forget about that. We're not going to talk about that pretty much the rest of today. So ignore that. But we do have this error term at the end, E of ij. And this is our total error. And this is going to be what we're focusing on for these next couple slides. So we could decompose that error term into these two terms, this eta j of A1, A2 plus epsilon ij. And once again, we're ignoring that first part. So eta j, well, if we're in the random effects framework, that's just our school level random intercept. So we've decomposed our total error into a school level random intercept plus this epsilon ij term, which is just our residual error. It's just the error that's left over. It's unexplained through the school. Now from random effects literature, we know that the mean of this random intercept, well, it's going to be mean 0. And for now, we're going to say the variance of that eta j term, well, it's the variance of the school intercept, so we're just, for now, going to denote it as sigma squared sub school. So we're just saying that's our school level variance. Our residual error, well, that's going to be mean 0 as well, and we're going to denote its variance as sigma squared res for residual error. So we know our total error, the variance of yij, is just the sum of our school level error plus that error that's left over, that residual error. Okay? So then our covariance between two school professionals I and K within school J, well, they're in the same school. That variance is just our school level variance of sigma squared sub school. So then the correlation between those two school professionals is our covariance over the square root of our variances. So it's sigma squared school over our total error, which we're going to say is just rho. And this is our intra-class correlation. It's the proportion of our total error that's explained through school level variation. Okay, so that's rho. Now you might say, why are we walking through all this math? I don't get how this is relevant for me at all. Well, bear with me. Because the decision we make about what the variance of that eta j is, the variance of our school level random intercept, that's going to determine the structure of our working marginal variance model, of our V of A1, A2. And while for now we've said it's just going to be sigma squared sub school, we don't need to make that assumption. But what do I mean by this? Well, let's say we're keeping it as sigma squared sub school. That led to rho, our ICC, which leads to the following working marginal variance model of sigma squared t, our total variance, times this 3 by 3 matrix. And there's a couple points here. Why is it 3 by 3? Well, this is just for a school with 3 school professionals. Okay, and this matrix we call exchangeable. So this will be an exchangeable working variance structure. So this exchangeable matrix has 1 across the diagonal, and then rho in the off diagonals, our ICC in the off diagonals. What is that saying? Well, if you look at the second row in the first column, well, that rho is the correlation between school professional 1 and 2. Once again, if you look at the first column in the third row, well, rho is the correlation between our first school professional and our third. Likewise, the intersection of column 2 and row 3 would be the correlation between school professional 2 and 3. So this is our working variance structure if we assume the variance of that school level intercept is sigma squared of school, and leads to our working marginal variance model of V of A1, A2. But as I alluded to, we don't have to say the variance of eta j is sigma squared sub school. Instead, you might say, actually, I don't think these outcomes are correlated at all. You know, the 3 school professionals in this school, well, one is a guidance counselor, one is a social worker, and the other one, never shows up or something. And, they don't overlap on any days. They're not in communication. Why should these outcomes be correlated? Well, if you say that's the case, then the variance of eta j, well, there is no school level variance. So we're going to set that equal to 0. And if we do and follow through with the math, well, then the correlation between 2 school professionals' outcomes in a given school is going to be 0. Which leads to the following working marginal variance model, which we call an independent structure. It's still sigma squared t, our total variance, our total error, But now we have zeros in all those off diagonals instead of row because they're uncorrelated. So if you think we have independence of school professionals, it leads to this working marginal variance structure, V of A1, A2. So you can see how the decision you made about how you think these school professionals are interacting with one another is going to affect what our variance structure looks like. But alternatively, you could say, I actually think the correlation is going to be, more involved. And what do I mean by that? Well, you could say the correlation of school professionals within a school is going to depend on which clustered AI that school received. So why might you think this is the case? So let's say you think the most intensive clustered AI in our SMART. So that was rep plus coaching and slower responders add-in facilitation. You think that clustered AI is super effective. And after all the school professionals receive that, they are all going to be offering the maximum amount of CBT possible. Well, if that's the case, those outcomes are going to be pretty darn correlated because they're all offering a lot of CBT. On the other hand, you might think rep only. Well, rep doesn't really do anything. And, because of that, certain school professionals are still going to be offering, more than others. There's going to be a little bit of correlation because they're in the same school, but rep hasn't really changed anything. So you would think that those outcomes are going to be correlated, but to a lesser extent. So if you think this is the case, then your variance of that school level intercept is not just sigma squared of school. It's sigma squared of school of A1, A2, because it's going to vary based on which clustered AI was received by that school. If you do that and follow all the math through, well, then your correlation of two outcomes within the school will also differ based on A1, A2, and we're going to denote this as rho of A1, A2, leading to the following working marginal variance model of sigma squared of t times, once again, an exchangeable matrix, but this exchangeable matrix is varying based on which clustered adaptive intervention we are looking at. So you can see how, once again, the decision you make about what's going on with school professionals within schools is going to affect what our working marginal variance structure is. And I do want to make one thing clear as well. If you are working with me or with Danny or Gabe or Mason, we're not going to tell you what the correlation should be or what the structure is going to look like. You're going to use your science and be like, based on what I know about interventions of this type or with my domain expertise, I think the outcomes are going to be correlated like this. And based on what you tell us, we will then provide you all with the working marginal variance model that best fits what you all think the science says the correlation should look like. I should also say these are just three possibilities: the exchangeable, independent, and exchangeable varying based on clustered AI. There are obviously many different types of structures you could have, and we're always looking at D3C to better capture this correlation structure. So don't feel limited by just these three. So that was the end of the modeling decisions, but you'll see how this crops up in the estimation method. I know you're like, yay, modeling's over, less math. This will be the last confusing formula I will show you. We didn't actually talk about this in Danny's module, but you can ignore all the parts in blue. What's going on here is to obtain our effect estimates, we generally solve an estimating equation, this equation, and there's now these two components that are in red. Why am I showing this? Well, these have changed. So yj is our vector of outcomes for school j. So if we have 3 school professionals within a school, this will be a 3x1 vector. So the point here is you can see how we have this nested data of outcomes nested within a given school. You can also see this Vj of A1, A2. This is our working variance structure that we've been talking about in previous slides. So you can see how the decisions you made about the correlation structure are going to factor into our estimation method. Now you might be worried because you're saying, well, Tim, I was kind of just spitballing there. I might not have told you the right correlation structure. That was just a hypothesis of mine. And I'm going to tell you, do not worry, because we've actually developed methods that will ensure your effects are still unbiased and your hypothesis test is still valid, even if you get it wrong. So even if the science that you brought to the table concerning those errors is incorrect, you're going to be okay. You're still going to obtain unbiased effect estimates. And you might say, okay, Tim, that's great, but I can't solve this equation to obtain the estimates. I can't do it in hand. I don't even know how to code it up in R. And I got more good news for you. I don't know how to, do it by hand either. But we have developed software that will provide these estimates and a bunch more for you by solving this equation for you. And we're going to get into that software in just a little bit, but briefly first we need to discuss sample size formula. So our sample size formula do change in clustered smarts in comparison to standard smarts, although they'll look pretty similar to you. So the formula I'm going to talk about today is for comparing two embedded clustered adaptive interventions. So that is AIM type 3. If you'd like the formulas for AIM types 1 or 2, we have it available in the handout section on the kd.space website. So inputs into our formula. M is going to be our number of units within each cluster. Delta is our effect size for the comparison. Rho is the outcome's ICC. R is probability of response to the first stage intervention. So I should also know this is a formula for a prototypical smart. So outputs from this formula will be big N, the total number of observations needed, probably more importantly also little n, the number of clusters needed for a given level of power. So here is our formula, and it's going to differ from what you've seen in two ways. So first we have this black portion, this 4z 1 minus alpha over 2 plus z 1 minus beta all squared over delta squared. That's just common to sample size formula. Nothing has changed there. But we now have two inflation factors. We have the inflation factor in red and the inflation factor in blue. And each of these should also look familiar to you on their own. So the red one is the inflation factor that's a function of the ICC and the cluster size. This appears in sample size formula for standard clustered randomized trials. As M is increasing, the total number of observations needed is increasing, although that doesn't affect the number of clusters needed. And then rho is your ICC, so as rho is increasing, you also need more clusters because your effective sample size is decreasing as rho is increasing. Then we have this smart inflation factor in blue, this 2 minus r. So this portion of the sample size formula also shows up in standard smart sample size formula as well. So this should be somewhat familiar if you looked at the handouts in the meantime. So what is this saying? Well, as your response rate is increasing, the number of clusters you need is decreasing, because they'll be better distributed throughout the different pathways. So a couple recommendations. First off, this formula is assuming that M is the same for each cluster. Obviously, that's not the case. Every school isn't going to have the same number of students or even classrooms or teachers in it. In practice, you can just use the mean number of individuals in a cluster for M, and hopefully they're not varying too much. The second recommendation, well, your response rate R might differ by first stage intervention option. And if that's the case, you have two options. You can either use an adjusted formula found in Niekamp et al., which is also in the handout, which I think is handout 3. Or you can just be conservative, which is always a good option, because if you're conservative, you are definitely going to have sufficient sample size to detect the given effect size at the given level of power. So to be conservative, you can just use the smaller hypothesized response rate for R. So if you think, R1 is 0.2 and R2 is 0.5, just use 0.2, you'll be conservative, you'll have sufficient power. So now that we've gone through all that difficult data analytics, math slides, we can get into the new software, which is hopefully exciting for some of you. So we've developed new software for clustered smarts in the form of an R package. This package will allow you to analyze data from a clustered smart using the function solve_smart. In solve_smart, one function is going to provide you with a ton of stuff that you can use to analyze your clustered smart. So it'll provide the various beta hat effect estimates and their standard errors, which will allow you to answer AIM types 1 and 2. It will also provide an effect estimate for the comparison of each of the embedded adaptive interventions, which is AIM type 3. And then for each of these embedded adaptive interventions, you will also have the mean, the variance, and the ICC. So you get all of this just from running a single function. So not only that, you're going to have a lot of tools and options to specify your analysis so that it fits with the science. So you can make decisions about the variance structure. So you could assume the variance is homogeneous across the embedded adaptive interventions, or you can decide the variance should be heterogeneous across the embedded adaptive interventions. So too with the correlation structure, you can set it to be independent. That was when we set that variance of our school level random intercept to be 0. It can be exchangeable. That was the initial example where we set the variance of A to J to be sigma squared sub school. Or it can be exchangeable and varying across the embedded adaptive interventions, which was that last example we looked at. So you have the option for all 3 of these correlation structures. You can control for baseline covariates as well, which I'm sure you will all very much so want to do. And then you also have a bunch of finite sample adjustment methods included in the package as well. With clustered smarts, as with clustered randomized trials, typically sample sizes are smaller because it's just more expensive to recruit a bunch of clusters. Because of that, you might have some bias because of small sample sizes. But Wen-Chu, who you might have had the opportunity to meet at Katie, has written a paper that I think is close to being submitted and also included all these finite sample adjustment methods into his package to make sure your type 1 error rates will be correct and you'll have proper coverage on your confidence intervals even though you have smaller sample sizes. So Wen-Chu's done some very, very cool work here. So now that I've mentioned how great it is, how do we actually use it? Well, you're probably going to have to install or write in all 4 of these lines to use it. You need to start by installing DevTools, the package, and then loading it in, and then installing the package from Wen-Chu's GitHub, and then loading this in. I also want to make the point that if this talk is not sufficient enough to explain how to use the package, there's also a vignette demonstrating its use on Wen-Chu's GitHub at the following link. So here is some simulated data that is from a simulated clustered smart. This is just the first 6 rows. There's many more, obviously. So the first variable is the school. You can see that 1 through 5 are all students from the same school of size 5. Row 6 is the first observation from school 10, which is of size 38. Ignore the differences in school sizes, simulated data. Then treatment 6 month, that column is our A1. So school 1 was assigned to A1 equals 1. School 10 was assigned to A1 equals -1. The next column is response. So school 1 was a non-responder, so the entire school gets a value of 0. School 10 was a responding school, so the entire school gets a 1 because the entire school is a responder. Treatment 9 month is A2, so school 1 gets A2 equals -1. School 10 was a responding school, so they aren't re-randomized. Then we have 2 baseline covariates. We have local temperature and math score, both standardized around 0. So temperature is a school level covariate. That's why it's the same for each of these students within the school, because the entire school has the same weather. Math score, though, is an individual level score. It's at the student level, which is why math score is varying for each student within a given school. Then we have our outcome Y variable. This is an individual level outcome as well, which is why each of these outcomes are varying for each student within the school. So to run a clustered analysis, you would use the following code using the solve smart function. This analysis is assuming an independent correlation structure. So first you specify y, which is your outcome variable. Then x is your baseline covariates of temperature and math score. Then this is important, you need to specify the ID of the cluster so that the package knows what the clustering level is. In this case, it is the school. So you specify that your school is your cluster ID. Then A1 was that treatment 6 month. R is your response, and A2 is treatment 9 month. And then you have the option to put in a variance structure. So here 0 assumes a homogeneous variance structure. 1 would be a heterogeneous variance structure. And then you set a correlation structure equals 0. That is for independent. And you get the following output here. So you get your effect estimates in that estimate column. That's your beta hats. So the intercept of 4.77, that's the grand mean. Then the estimate for A1, that's your beta 1. And that helps you answer type 1 primary aim of 2 times beta 1 hat equals 2 times 1.405 equals 2.81. That is the effect of the first stage of the intervention. 2 times the coefficient on A2 of 0.26 equals 0.52. That would be the main effect of the second stage of the intervention. The term next to that I of A1 times A2, that's your interaction effect. And then we can kind of ignore the baseline covariates. So on top of those effect estimates, we are given the standard errors, confidence intervals, t-scores, and p-values. The p-value that effect estimate is different from 0 in this case. So we do have a significant effect of the first stage of the treatment because our p-value of 2.24 times 10 to the negative third is less than 0.05. Alternatively, we could have chosen an exchangeable correlation structure. So everything else is going to be the same. Just now we set correlation structure equals 1 for exchangeable. And if we wanted exchangeable and also varying based on adaptive intervention, we would set correlation structure equals to 2. So these parameters, estimates, let you get at the first 2 primary aims. But we have more. So if you use this line, you can get the mean under each of these 4 adaptive interventions, along with an estimate of the variance and the ICC. So since we chose a homogeneous variance structure, that's why the variance here is the same across the 4 embedded adaptive interventions. And since we chose an exchangeable correlation structure, we have the same ICC across all 4. If we chose an independent, this ICC would be 0 for all 4. And if we chose exchangeable and varying based on clustered adaptive intervention, this ICC would change for all 4. Likewise, if we chose a heterogeneous variance structure, the variance would be different for the 4 embedded AIs as well. So from these parameters, or these effect estimates, we can compare embedded adaptive interventions, and you don't have to do that by hand. The package has done it for you. So if you do model $ comparison, it provides comparisons of all of the embedded adaptive interventions. 4 embedded AIs leads to 6 comparisons that you could find here. So if your primary aim was to compare the most intensive AI of 1, 1 with the least intensive of -1, -1, you would go to row 3, see an effect estimate of 3.36, a p-value less than 0.05, so a significant difference between these embedded AIs. 3.36 does happen to just be the difference between AI 1.1's mean and AI -1, -1's mean from the previous slide. So that is how the package is working. We do have future work related to clustered smarts. So we are working on 3 and 4 level analytic methods. So for example, maybe observations nested over time within students, students within classrooms, within schools, etc. That's what Gabe's poster was about at Katie. I think he's getting close to submitting a manuscript for that as well. We also have sample size corrections that we're working on for clustered smarts. That's what I was talking about with Winshu, who I believe by the time you watch this will have probably submitted his manuscript as well. We are also working on multi-level smarts, where the sequence of randomizations occur at multiple levels. That is what I am primarily working on. A multi-level smart can be used to optimize a multi-level adaptive implementation strategy, which Danny mentioned briefly, or just multi-level adaptive interventions more broadly. What do I mean by that? Well, the initial treatment could occur for the entire cluster, but then response status and subsequent treatment would be at the individual level. So it's students nested within classrooms. So related to that, we're excited about using clustered adaptive interventions and multi-level adaptive interventions to engender positive spillover effects to improve academic outcomes, and developing methods to quantify and understand such spillover effects. So thank you. We hope that this has been interesting for all of you, given the natural clustering that occurs in education settings, and we expect these clustered smarts and multi-level smarts to have a wide applicability in your field. If you have any questions, you could email me, but there will also be an office hours question answering session. I think it's April 18th at 3 p.m. Eastern. But I think Gillian or Ian will probably have included that in an email. So I'd love to see any of you there if you happen to have questions about this. Thank you very much, and I will hopefully see you in a month.